The sister counterpart to reduction is called oxidation, right? So oxidation is basically the opposite of reduction. So when I take a look at oxidation, we are increasing the number of C to O bonds. Alright, so if I take a sugar, and let's just start off with an aldose. I have a C double bond OH here, and then we have a CH2OH down here below. And let's do OH group on the right, OH group on the left, OH group on the right, and OH group on the right. If I look at this structure and I ask you to name it, this is one of those structures that you should know by heart, and this is right, left, right, right, and that means that this is glucose. So here is glucose. Not only that, but this OH group is over to the right hand side, and therefore this is called D-glucose. Okay, so I need to take D-glucose, and we're going to undergo a reaction, an oxidation reaction. And an oxidation reaction, again, means you increase the number of C to O bonds. Well, we can't really increase the number of C to O bonds up here at the top, right? That oxygen already has 2 bonds. That's where it's happy. Its formal charge is 0 at that position. So we don't really want to put a third bond here between carbon and oxygen. That's bad news. Okay, so maybe any of the other compounds would be fair game. Carbon to oxygen bond in every single spot. So there's a carbon to oxygen bond here, and one here, and one there, and one here, and there's actually one down here at the bottom. Okay, so I'm just going to redraw this one here at the bottom in a different format. This has a carbon on it, and this carbon has an oxygen that has an H, and this carbon also has a hydrogen, and it has a hydrogen here as well. Okay, so there it is. There's the sugar. We need to figure out if something's going to oxidize, which carbon is going to oxidize. Well, you need to think about geometry here. You need to think about the one that's more exposed here. And you need to think about the one that can maybe become a little bit more reactive. And that's the one on the very end, not the ones in the middle. So in these oxidation reactions, we are going to be looking at this CH2OH group down here at the bottom of these traditional Fischer projections for sugars. And what goes on is that this bond will basically oxidize. Okay, so what does that mean? Well, the bond up here at the top doesn't change. And all of the bonds on the center of the backbone, they don't get touched. They stay the same as well, all the way through. Down here at the bottom, this is a CH2OH group. This is the part that gets oxidized. So we need to create a double bond between the carbon and the oxygen. So again, let me redraw this to maybe allow this to make a little more sense. So I see a hydrogen here, and a hydrogen there, and an OH group here. So we need to create a double bond. And when I do that, well, this oxygen now has 3 bonds. If I leave it that way, it can't have 3. I need to get rid of one of these hydrogens. So I get rid of one of those hydrogens. This carbon now has 1, 2, 3, 4, and 5 bonds. It can't have 5 bonds, so I need to get rid of one of these hydrogens as well. So I erase one of those, and now everybody is happy. And look at what we've done. We've taken the CH2OH group down below, and we've converted that over to a C double bond O. Alright? So that's really the whole story about oxidation in a way. The problem, though, is that it just doesn't stop there. Depending on the strength of the reagent that is undergoing or allowing this oxidation to happen, depending on its strength, a couple of things will go on. Now, in both of these scenarios that we're going to talk about, we are increasing the number of C to O bonds. Well, we increase the number of C to O bonds by creating the C double bond O group down here at the bottom. But that's not the only C to O bond that gets included or gets increased, because actually these oxidation reactions will take this aldehyde group and it will sandwich an oxygen in here as well. So now we get this carboxylic acid functional group that shows up. And if the C double bond O forms down here at the bottom, well, that also gets an oxygen sandwiched in between the carbon and the hydrogen. So this gets a carboxylic acid functional group down here as well. Okay, so there is a proper term that we use to describe a structure that has many OH groups on the carbon backbone and a carboxylic acid group up here at the top and a carboxylic acid group down here below. So let me just write that here. Carboxylic acid, in case you don't know that functional group. Surely you do. And then these things are called alderic acids. So we know where the acid term comes from. The acid term comes from because it's a carboxylic acid. Alderic, well, kind of funny thing happens here. You can kind of look at the word al coming from aldehyde, even though we would use it to describe ketones as well. The problem though is that ketones typically don't undergo oxidation reactions. That's a separate story we'll get into in a minute. But alderic acids, the way that I like to remember this is alderic, well, the R means there are two COOH groups, right? One on the top and one on the bottom. Why does that matter? We'll see that in a couple of seconds. What reagent makes this undergo the reaction that we've just described? We need something that will promote oxidation to go forward, and we need a strong oxidizer. So a very strong oxidizing agent is nitric, HNO3 with a little bit of heat. So if I take a sugar, I add nitric acid to it, and I heat it up in a test tube, what will happen is that my C double bond O up here at the top, that turns into a C double bond OOH, and the CH2OH at the bottom turns into a C double bond OOH group. So two carboxylic acids, alderic acid. There are two groups as far as carboxylic acids go on the structure. Alright, well, I can do the same thing but use a weaker reagent, and it will do something kind of similar for me. So I can take the same sugar, we'll start off with glucose, so right hand, left hand, right hand, right hand. So here's the structure of glucose, and I can oxidize this as well, but only target one and not both. So this C double bond O changes into a C double bond OOH. Only one carboxylic acid gets formed. The structure down below, the CH2OH, that doesn't get touched in this example. So the reason is because this reagent is going to be weaker. So it can only put one O group on the molecule, not two. Well, what reagent does that? Well, this is bromine. Bromine is a wonderful reagent that we can use to promote this oxidation to go forward, and it's weak enough to only do this once. I'll talk more about bromine in a minute, but this structure also has a certain name that it goes by, and this is called an aldonic acid. And again, acid means carboxylic acid, C double bond OOH, right? Al means kind of coming from an aldehyde, if you want to think of it that way. And then this onic, well, think of this onic as one group. So now you kind of see why I mentioned and stressed alderic a while ago. Look at this. Aldonic acid, alderic acid. Aldonic acid has one carboxylic acid group. Alderic acid, there are two carboxylic acid groups in the molecule. So that's a very good way to keep these two things straight. Okay, so what's the story with bromine? Well, as you know, if I had a test tube with bromine, well, let's say that there's a sugar solution in here first. So this sugar solution is clear, right? So sugars are typically clear. Some of them have a slight color to them. Some of them are kind of yellowy, but most of the time they're going to be a clear solution. What happens is that if I add bromine to this solution, bromine is a liquid and it's orange, right? So what goes on here is that if I add this orangey bromine to the test tube, once it hits the sugar, it will begin to oxidize the sugar. The bromine is used up. So if I've got a test tube, two of them, and this test tube has a solution in it, and I put Br2 in one of them, well, the orange bromine color goes away when it hits the carboxylic acid, or when it makes the carboxylic acid, right? The bromine, the Br2, breaks apart, and this bromine begins to allow the carbohydrate to undergo oxidation. So if I take drops of bromine in a sugar solution and that orange color disappears, then this is confirmation that I have an aldose, if I know that it's some type of sugar. If this is a ketose, however, the ketoses do not undergo oxidation. So this bromine is a very good qualitative test for me, because if I add bromine to a solution of a sugar and the orange color stays and it doesn't disappear, then that is a very good indicator that I have a ketose instead. So bromine is very specific to the aldoses. It cannot oxidize ketoses or just normal alcohols. It can't go forward. And this is a qualitative test that we can use in the lab to distinguish between an aldose and a ketose. Again, if I know there's sugar solutions and I take bromine and I add a drop or two to an aldose, it should go clear because my bromine is being used up for this oxidation. If I take bromine and add it to a ketose, that orange color does not disappear. It stays in the test tube because oxidation is not happening. It's not occurring. Bromine is not getting used up. So these structures, if I use nitric acid, alderic acids are basically going to be formed. Bromine, aldonic acids are going to be formed. And truthfully, if I take nitric and add it to a ketose, well, nothing's going to happen there either. No oxidation will take place. So they're just not very specific at all. Dilute nitric acid is stronger than bromine, but the problem is that ketoses typically don't get reacted with those as well. So no reactions to a ketose as far as oxidations go. Aldoses are the ones that we're after. So that's it of reduction and oxidation. We could have made this a little bit more complicated. I could have thrown in mechanisms. I could have thrown in some exceptions, but we're not going to. We're going to kind of keep it at face value, keep it at that, and just realize these are the structures that can be made, and this is how they're relevant.